Yeah, so long title, but in this talk I'll be showing you how Bayesian inferences can be used to decide how to eat healthy. That's the whole point. So my name is Jari Turkia. I come from University of Eastern Finland, and I also run a team of analytics in CGI, and we use Stan in both places, and I try to push Stan use in production also and industry use when we use Stan for healthcare modeling, basically, most of the time. And we study personal nutrition. This is what it's about, and especially how to infer diets for better personal health. And this is the concept, the graphical model, basically what we are talking about today. So we assume that we can predict concentrations, cholesterol, insulin, glucose, whatever, in the blood based on the nutrient intake in your diet. And of course, there might be different goals for the personal nutrition. You may want to gain muscles or lose weight or whatever, but nevertheless, the homeostasis, the balance of the concentrations, it's important anyway, and it's a good measure of health, and that's the response we are looking for. And before we can do any diet inference, we need to model how the nutrients affect the concentrations. And this is what basically enables the whole personal nutrition. The fact that we all react to nutrition or the diet differently. The differences may be small, but there are lots of bigger differences and maybe some even opposite effects on nutrients. And before we can do the inference, that's the main topic of my talk. Let's talk briefly about the nutrition effect model. That's a hierarchical model. The data we use consists of repeated measurements, personal measurements from food records, and the matching laboratory results of those concentrations. And that forms the personal level of the model or the hierarchy. But the hierarchy can be nested to treatment groups, like the type of dialysis for the kidney patients that we study. Then we can analyze, does the treatment affect how the nutrients affect your cholesterol level or albumin level, which is important for kidney patients, for example. And the model is also a multivariate, so we are always having the predicting from same diet, but we are analyzing different concentrations, how it affects your cholesterol level and insulin level, and simultaneously. And in this talk, I'm going to skip the formulation of our hierarchical model, but I wanted to point out that when you are doing a multivariate hierarchical model, you end up with a correlation matrix that has this block diagonal structure, when the diagonal has the blocks of your normal univariate correlations of responses, and the cross response effects are on the across diagonal, and it's a diagonal matrix, and the correlations are transposed across the diagonal. But I can talk about this later if anyone wants to dig into. But the main thing is the inference model. And if you look at the graphical model, is the same thing that we used for predicting the effects, but now we are doing the inference with the same model. And two things that happen. First, on the right, we constrain the concentrations to have some lower upper level for every concentration. And day two, the concentration limits, they vary based on age and sex. So that's a moving target also. And then we turn around that arrow from concentrations to nutrition, and we want to estimate those intake levels of Q here. And then we split the predictors in the fixed part, like medication and sex, that we don't recommend to change. And then there are the adjusted nutrient intake levels that we are inferring. And also, in the next slide, yeah. And we are building here a conditional mixture model where these inferred nutrient intakes, they are given a prior distributions from general public recommendations. So the basic goal of our research is to personalize the general recommendations. So they are good, but they are targeted for broad audience and bigger public, and provide general trends. And generally, they are not like necessary fact for your personal health. And what we are building here is a mixture model that tries to balance out this whole graphical model, so the diet and the concentration limits, and put on some personal preferences that you might have. We also introduced quite a big number of hyperparameters that you can use to tune to model those blue balloons there. And let's now look this construct more closely. So when we started out, we had two major problems with the model. First off is the initialization, and then the other problem was the identification. So the usual case is that when we have the intake between the limits, and then the usual case is that there are so many options that have equal probability that they don't identify the recommended intake levels properly, and that leads to unidentified model and problems with estimation. So let's look at our solution for the constraints first. Here's some theory. So what we want to do formally is to have enough of the probability mass between those concentration limits for all of those concentrations that we consider. Our data, we have multiple data sets, but they tend to have like from 3 to 5 different concentrations that we are considering simultaneously. And the intuition is that we need to have enough of these intake predictions between those, or the probability of the intake predictions or the concentration predictions between those limits. And the intuition is that the distribution is pushing against the limit, and when you have the narrower distribution that is more confident, you can have a wider range of intake more safely. And if the prediction it's not confident and it's wide, then you can only have this little range of intake that you can recommend safely. And how do you calculate this? Okay, the basic statistics is to calculate the quantile values of the concentration points. And now Stan has a quantile function that could be used for this, but when we start building this, we consider that it might be slow to calculate the quantile values during the sampling. And we decided to transform the limits. And we can do that because the distributions of the concentrations are modeled before the inference part. They are modeled already when we are estimating the effects. so we can just adjust the limits and see what are the expected concentrations or the expected values of the concentrations that match those original limits, and then we can just make inference for those expected values. But this is still a non-smooth step function that it's not going to work with Stan or with gradient-based things. So our smooth solution, it's also like usual stuff, is to use logistic sigmoids that we place at the location of those expected values that match the limits. And they have some nice properties. So the sigmoid goes from 1 to 0 when the limit is reached. So then we can easily calculate that do we meet all the limits that we need to. Just we know that we are having considering, for example, 3 different concentrations, and we know that we need to reach or go between lower and upper limit of each of them. So we just count from 1 to 6. We need to find 6 or reach the 6 limits. And then again, we have this one of the hyperparameters adjust the steepness of this limit. So if we are loosening the steepness a bit, we can have a support for all the intake that we are giving from that is coming from the priors. Let's now look at some code and results that we have. So the priors first. So the priors we got from the public recommendations. So basically we are just taking a uniform distribution, just the adequate lower limit and upper limit of any healthy intake. And then we are throwing in normal distribution that puts a little dent so we can prefer the middle point there if needed. And this is the implementation of the constraints. So we are calculating the expected values and counting the points or the reached limits that we have there. And we are using a normal distribution to see that if we are really meeting all the limits, and we want to do that. And that's the 2 times the concentrations point that we want to meet. And this results, this distribution, and we can see that we can find the diets that result concentrations between the limits. And it's okay, but as I said, these lead to divergent transitions and the problems because the equal probability of the recommendations. And then we add the personal preference that is only considered after all the limits are reached. Then we want to find some most probable point, some mode for the posterior. And we are also building here this in-range coefficient that implements the conditionality. And here there's the preference error function in Stan. Then you can implement however you like, so that just needs to be ambiguous, like the current diet. So in this analysis, we are seeking diets that are close enough for your current diet, and we change that only if it's needed. And this results well-defined modes for the concentration predictions. And recall that all these points come from very high dimensional joint distribution that captures and at this example, 13 different nutrient intake levels and also those concentrations. and that's preference coloring. It's from the intake part of the mix. And finally, here are some intake recommendations that we end up. So on the top row, there's you can see the dashed line is the current intake, and it's really higher than it should for this patient to have the healthy concentrations. But then again, on a lower row, the fiber and protein, they are good. So you don't need to worry about your protein intake, and the model just aims for your preference. So the conditional mixture works here. So it only changes the intake that needs to be changed. Okay, and my final result slide is the bigger picture. Here is a bunch of kidney patients, and you can see from the lines that there's lots of personal variability there. The top line is the baseline. That's the concentration prediction based on those fixed things that we have. There's medication and sex and the baseline, and then we are just summing up the linear predictions from those recommended intakes, and on the bottom line we have the predicted concentration levels. And the black line is our running example here, and this dashed line is for example, the albumin lower level that it's problematic for the kidney patients. You can see that they are all struggling to reach it, even with our recommendation tool. But we hope this can have some benefits for the practitioner nutritionists to have some statistical tools for making personal preferences. Okay, thank you. So